Hey guys, today I want to go through how to identify the correct Lewis structure, the shape, the bond angles, whether a substance has dative bonds, and the type of hybridization using 3 different examples so we can get practice doing each of these things. So let's start with the xenon tetrafluoride and determine the best Lewis structure. First, I wanted to figure out how many valence electrons there should be in this structure. So I know that xenon has 8 valence electrons and fluorine has 7 valence electrons. But there are 4 of them, so that gives me a total of 36 valence electrons. So let's start sketching this out and see how many are really involved. We have our xenon, that would be the central atom, and then our 4 fluorines would surround that atom. Now each fluorine, since it's got a single bond already, can have 6 more electrons, or 3 more lone pairs on that fluorine. If we count this up, the 6 valence electrons on each fluorine plus the 8 electrons involved in the set of 4 single bonds actually only totals 32 electrons. So here I have a difference of 4 electrons. Where am I supposed to put those? Well, xenon, fortunately, can have an expanded octet, and so we're just going to put those 4 electrons on that central atom. So that's going to lead to an interesting shape, because to determine the shape, you have to look at the charge centers. So the charge centers include, of course, each bond, but it also includes each lone pair. So that is actually a total of 6 charge centers, which basically means we are looking at the octahedral set of shapes. It's not going to actually be octahedral because there aren't 6 atoms attached to it. So if I have only 4 atoms, then it becomes trigonal, square planar, 4 corners, square planar. When I have 2 atoms replaced by a lone pair, it'll happen in that axial set of atoms. So my remaining 4 atoms would form a perfect square planar. The bond angles would actually be exactly 90 degrees, not less than. Usually when you have a lone pair to bonded pair interaction, they do push more and you get smaller bond angles, but this is an exception since that lone pair is on the top and bottom of the plane. The plane is not going to be pushed one way or the other. There's no curling like there is if only one of these was a lone pair. So that means that my bond angles are going to stay 90 degrees. Now let's look at whether or not there are any dative bonds. So for that, we want to consider how many electrons are actually on the atom right now and compare that to how many they brought in the first place. So xenon, we already said, had these 2 lone pairs, those 4 electrons, and then it also would have 1 electron involved in each of those single bonds. That's a total, 4 plus 4, of 8. Which it originally had. So xenon pretty much has what it put in. Fluorine has the 6 electrons around it, plus 1 from the lone pair, or I'm sorry, 1 from the single bond. And so that is a total of 7 electrons. Again, it has what it brought in. So there are no dative bonds in the xenon tetrafluoride. The last thing we want to look at is the hybridization, and for that I'm going to redraw this, kind of clean it up a little bit. We had our xenon in the middle, attached to the 4 fluorines. And then the xenon had the 2 lone pairs, and each fluorine had 3 lone pairs. And you would have that on the other atoms as well, of course. So let's start with xenon's hybridization. Xenon has 2 lone pairs. It also has 4 sigma bonds. So a sigma bond, if it's a single bond, it's automatically a sigma bond. If it's a double bond, 1 sigma, 1 pi, and if it's a triple bond, 1 sigma and 2 pi. The sigma is the first bond that occurs in the plane between the 2 atoms. Those electrons are then localized, they're stuck in between those 2 atoms. So that's what has to be degenerate, is those single atoms, or I'm sorry, those single bonds. The lone pairs would also have the same energy as the single bonds, and so basically we have 6 orbitals that we need to become degenerate. So you start at the beginning with an s orbital, but there's only one s. Then you can bring in your p orbitals, and you can have up to 3 of those. So with one s plus the 3p, now I have 4. I still need 2 more, so we have to move on to the d orbitals and involve 2 of those for a total of 6 orbitals. So you're determining the total number of lone pair and sigma bonds to figure out how many degenerate orbitals, and then create that many orbitals starting at the lowest energy and working your way up. So the xenon is going to be sp3d2 hybridized. Usually they only ask about the central atom hybridization, but you can determine it for the other atoms as well. So let's do fluorine just for a little extra practice. We have 3 lone pairs for fluorine and only 1 sigma bond. So that is a total of 4 degenerate orbitals needed. So we start with the s and then bring in the p, and we would need all 3 of the p's in order to get a total of 4 orbitals here. So the fluorine would be sp3 hybridized. So that finishes our xenon. We've got a valid Lewis structure. We know it is square planar with 90-degree bond angles, no dative bond. The xenon is sp3d2 hybridized, and the fluorine is sp3 hybridized. Now let's move on to carbon monoxide. Make a little room here. So when I know I have atoms that cannot have an expanded octet, you can use needed, available, shared. You may remember this trick from Honors Chem, but be careful, you can't use that with expanded octets. It doesn't work. So really it only works for those couple of atoms that we know don't have an expanded octet, like nitrogen and carbon. But think about how many molecules actually have those atoms as their central molecule. It comes up a lot, so it is a useful tool still to have. So needed is going to be 8 for everything except for hydrogen. So here it's going to be 8 for both the carbon and the oxygen for a total of 16. Available, carbon has 4 valence electrons and oxygen has 6. So we have 10. So to find out how many electrons are shared, we'll subtract them. And then I like to cut that number in half to figure out how many bonds, since there are 2 electrons in every bond. So this little trick allows you to calculate exactly how many bonds in the molecule. So I'm going to sketch my carbon attached to oxygen and give it a triple bond, because that molecule has to have 3 bonds. And then to complete the octet, we'll put 1 lone pair on either side. So this shape, of course, is linear. What else would it be? You may see some people, some answer keys out there would have this bond angle labeled as 180 degrees. I don't like to give it a bond angle because an angle you really need 3 things, and we don't really have a third. Like carbon dioxide, we could say there's a 180 degree angle between the 3 atoms, but so I'm just going to say that there's no angle, but it would be okay to say 180 degrees. Either way is fine. This is a really good example of something that does have dative bonds. So let's figure out how to determine that. First of all, I'm going to start with my carbon. With its lone pair would be our first 2 electrons. And since it only brought in 4 valence electrons, it can only provide an electron for the first sigma bond and 1 of the pi bonds, the first 2 bonds formed. Then carbon doesn't have any more electrons to give. Oxygen, on the other hand, brought in 6 valence electrons. So that would be its first 2 on the lone pair, 1 to match the carbon electrons to get us up to 4, and then the other 2 would actually be that third bond, or the second pi bond. There is a way to redraw this once you determine, hey, yes, I have a dative bond. Yes, it is dative. In order to do that, we start drawing the structure the same as we would for a normal Lewis structure. But for that dative bond, you want to show that the electrons are being sourced from the oxygen in order to make the bridge to carbon. So you would actually draw that with the arrow if you were asked to show that coordinate bond. So that's how you would do that. And then finally, let's look at the hybridization. We have 1 sigma bond and 1 lone pair on either atom. You could say the same thing, same thing for the oxygen. 1 sigma bond and 1 lone pair. So if I have 1 sigma and 1 lone pair, That's a total of 2 degenerate orbitals needed. So that would only be one s and only one of the p's. So both of these atoms are sp hybridized because we only need 2 degenerate orbitals, one for the lone pair, one for the sigma bond. The pi bonds are not hybridized, and so they do not count for the number of degenerate orbitals needed. They actually do have a higher energy. All right, so that wraps up carbon monoxide. On to our last example, the chlorine trifluoride. Let me make a little more room. So chlorine, we know, can provide 7 electrons, and fluorine also 7, but there are 3 of them. So that is a total of 28 electrons that I need to place in the Lewis structure. So let's start by drawing chlorine in the middle, and then attach 3 of the fluorines. Around each fluorine, since I have to have a single bond to connect the chlorine to fluorine, I'm going to be able to add 6 electrons. So the electrons that I have right now, just in these lone pairs and the original 3 single bonds required to hold the atom together, still only total 24 electrons. Chlorine doesn't have a complete octet, so yeah, we can give it that, but okay, now we're up to 26 valence electrons. I still have 2 more that need a home. So chlorine's actually going to have to house 2 pairs, 2 lone pairs in order to get those 4 valence electrons all to have a home. So this would be our Lewis structure for the chlorine attached to 3 fluorines, but with 2 sets of lone pairs, which is going to drive the shape because now I have 5 charge centers. Each bond would be a charge center and each lone pair. I have a total now of 5 charge centers, which means the basis for my shape is the trigonal bipyramidal shape. And if it had all 5 as atoms, that would be its shape. But again, we only go based on the atoms themselves. So when I have 2 lone pairs, it actually makes it T-shaped. It replaces 2 on that plane. So this is going to be a T-shaped molecule. The catch is these will influence the repulsion. Now they will be pushing more on the bonded electrons. It's not even like it was with the xenon tetrafluoride. This one is uneven, and so it is going to have a bond angle of less than 90 degrees between the 3 atoms. That angle is going to close because of this repulsion. So we have lower bond angles. So let me redraw this so we can look at dative bonds and hybridization. So we had chlorine in the middle and our 3 fluorines with 2 lone pairs on the chlorine. And of course, every fluorine would have the 6 electrons around it. So in order to look at the dative bonds, we have to compare the number of electrons on it now compared to how many electrons each atom brought in the first place. So fluorine has the 6 electrons in its lone pairs plus 1 from the bond for a total of 7, which is exactly what it contributed in the first place. Fluorine, on the other hand, oh, I did that backwards, sorry. That was the fluorine we just figured out. But that's also, fluorine also brought in 7, right? So then chlorine has the 4 electrons in the lone pairs plus 1 of each of the single bonds. That's also 7. So chlorine's also ending up with what it contributed in the first place. So when those numbers match, we know it is not a dative bond. So the only one that was dative here was the carbon monoxide. All right, now for the hybridization. Now we've got to look at the sigma bonds and lone pairs for each atom. So let's stick with red. Let's do chlorine first. Chlorine has 1, 2, 3 sigma bonds. The single bonds are always sigma bonds. And then it has 2 lone pairs. Sorry. So the 3 sigma bonds and the 2 lone pairs means I have a total of 5 degenerate orbitals. I need 5 orbitals of equal energy. So you're going to start with your S, use 3 P's, and now we're up to 4 orbitals. We still need 1 more, so it'll be, include the D. So it'll be sp3d hybridized. To look at it for the fluorine has just the one sigma bond, but it also has 1, 2, 3 lone pairs for a total of 4 orbitals that I need to become degenerate. So you'll have one S, all 3 P's, and that will total the 4. You don't need any D this time. So the fluorine is sp3 hybridized, whereas the chlorine is sp3d hybridized. That central molecule hybridization is kind of what drives the shape here too. So you want to make sure that you have 5 orbitals when you have 5 charge centers. You can kind of use that to check yourself. Nice little trick. All right, so I hope this helps. To determine the Lewis structure, you have to make sure that you have enough electrons. Exactly the number of electrons is provided by the valence electrons each atom brought in. If you have extra electrons after you've completed everybody's octet, if the central atom has a 3rd energy level, then you can put the extra electrons. We call that an expanded octet. The shape is determined by the number of charge centers, but then you have to adjust that shape in order to represent only the atoms. And if there are lone pair to lone pair interactions or lone pair to bonded pair interactions, usually you'll see a smaller bond angle. You just have to keep in mind sometimes that can balance out like it did with our first example. To determine if there are dative bonds, you have to compare the number of electrons the atom has to how many valence electrons it originally brought in. If those numbers match, it is not a dative bond. But if you have one atom providing more than the other, like we did with the carbon monoxide, then you do have a dative bond, also known as a coordinate covalent bond. And you would redraw that with the arrow. And then last, to determine the hybridization, you have to total the number of sigma bonds, which are the single bonds or the first bond out of a double or triple bond, and then add the number of lone pairs. Those are also going to be equal energy. That'll give you the total number of orbitals you need, and then you start at the lowest orbital, S, and build your way up to the D as needed. If you don't have more than 4 orbitals, you won't have a D orbital. So this is just sp3 hybridized, whereas this one was sp3d hybridized. All right, guys, I hope that helps.